Good morning. This class talk, call it what you want, is a talk on black holes for absolute beginners, okay? Actually, I gave this talk at 8th grade level in my son's school. So all you need is basic algebra. You know, if you can find simple interest on some number, or if you can work out the tax on your check in the diner, then you can follow this, okay? All right, but before I do it, I want to give a little bit of the history. I have a bunch of names here, and I always like to include the people involved in this when I'm studying it or talking about it, all right? So, you know, why am I beginning with Eratosthenes? Eratosthenes lived between 276 and 194. Is he getting younger? No, it's BC. Okay, BC. And I'm beginning with there because that was, as far as I know, the first time anybody realized that the Earth was a sphere, okay, with a certain radius. Now, Archimedes had worked out ways to find the volume of the sphere. I could bring everybody in. I could bring Archimedes in. I'm not going to bother. I'll begin with Eratosthenes. But the big leap ahead really comes in with Galileo, 1564 to 1642. Then we begin to look at free fall and the idea of mass and the beginning of the equations of motion, which were formulated by Isaac Newton, of course, the three laws of motion. We'll talk about that. Isaac Newton lived Galileo was born in 1564 and died in 1642. But wait a minute, who was born in 1642? Some people think it's 1643. Isaac Newton, the year Galileo died. Is that reincarnation or what? I don't know. So Isaac Newton lived to 1726, and during his lifetime there was a very important number that was never discovered, which allowed real calculations to be made using his law of gravity. That number was measured by Henry Cavendish, the richest man in England, who lived between 1731 and 1810. He used a torsion balance invented by John Michel. John Michel is the beginner of black holes, or dark stars. I do not like this term. It was coined by John Archibald Wheeler of Wheeler, Misner, Thorne and Wheeler fame, and other things. Wheeler was Feynman's doctoral supervisor, and I'm going to talk about that in a minute, right? We can all trace our physics heritage. I call it natural philosophy. Our education heritage, if you like, or mentorish heritage back. And mine seems to go back on the German side. I'll show you why that is in a minute. But I couldn't get any trace to Feynman. So, yes, I could, indirectly, because he worked on the Los Alamos project with David Bohm, my first physics teacher. So, let's continue. Laplace also had a hand, John Michel lived between 1734 and 1793. I have those on the board. Pierre Laplace, Simon Pierre Laplace, great mathematician. Laplace's equation, partial differential equation. Okay, Laplace also had some say in the idea of these dark stars. George Bernard Riemann, the founder of actually, not only entirely him, a lot of people are involved with him. Riemann, I call him Riemann, was Carl Friedrich Gauss's student, really, so it begins with Gauss. Without Gauss, we wouldn't have Riemann, we wouldn't have Riemannian geometry. Riemann, 1826 to 1866, gosh, he only lived to be 40. Einstein, the Albert, 1879 to 1955. I think Marcel Grossmann began to teach him Riemannian geometry to formulate the general theory of relativity. Okay, that's coming up. Carl Schwarzschild. Let me just check to see if this is running. Yeah, it's running. This talk might go on a bit longer than usual because I figured out how to go over 28 minutes. All right. Einstein died in 1955, 2 years after I was born. Schwarzschild, Carl Schwarzschild. 1879 to 1955, that's not correct. Wait a minute. When did he live or die? 1873 to 1916. That was Einstein's year. Okay. J. Robert Oppenheimer. Now, in the 20th century, many people did work on this idea of black holes. John Wheeler himself. But I like to put in J. Robert Oppenheimer as a beginner because he took it seriously in the 30s. And there's a thing called the Oppenheimer-Volkoff limit. All right. A student of Robert Oppenheimer's was David Bohm, who was one of my first physics teachers in Birkbeck College, a great college of the University of London. Good for part-time students. I was working full-time, and I put my foot in the door first into physics in Birkbeck College by going there in the evening. And David Bohm, I have to say, was a terrible teacher, but a real nice guy. Subramaniam Chandrasekhar. Wait a minute. How can I link Chandrasekhar up to Queen? I can in a minute, right? All right, so that's where we're heading, and I like to link all these people. I seem to go into what's my heritage in terms of academic genealogy. Okay, well, David Bohm was my first teacher, as I mentioned, in Birkbeck College. Where am I? Me. Now, David Bohm's doctoral supervisor was Robert Oppenheimer. Robert Oppenheimer's doctoral supervisor was Max Born, a founder of quantum mechanics. His granddaughter is Olivia Newton-John. How about that? She sang in Greece, all right? She was part of the disco era, Bee Gees. Olivia Newton-John, I didn't like that movie much, it doesn't matter. Who was? John Travolta, yeah. Olivia Newton-John is Max Born's granddaughter. Max Born's dissertation supervisor was Carl Runge. I did some work on the Runge lens vector and I lost it. I wanted to do a class on it for you guys. It's an interesting calculation. All right, a couple of steps backwards and we arrive at Carl Friedrich Gauss, whose student I already said was George Bernard Riemann. But Runge was Gauss's student, so I'm trying to trace my heritage back to Gauss. Yeah, that's a good start. Runge, Born, Oppenheimer, but through Bohm and down, I guess, at the last dregs. I'm not dead yet, so I didn't put any years in. I put in years for all these guys. Now, let's look at the other end of the story. Chandrasekhar. Who was his doctoral supervisor? His doctoral supervisor was Ralph Fowler. Ralph Fowler had a lot of great students, including Paul Adrian Morris Dirac. Another one of his students, Irish guy, Sir William McRae. Who was Sir William McRae? He was a great astronomer. Fowler was actually a great astrophysicist. Now, William McRae's student was Michael Rowan Robinson. And who did he supervise? He only has one student. Brian May. Who is he? He's the guitarist out of Queen, all right? So we have two rock stars in here, Brian May and Olivia Newton-John, and they're all connected. How about that? All right, so let's get talking about the black holes. Black holes, dark stars. Fowler, Dirac, McRae, Robinson, May, Chandrasekhar, and all that stuff up there. They're all related? No, but you can make them related. Oh, there's more. I just kept it simple. Now, I'll keep these ones on the board. Now, I'll just begin to talk about Eratosthenes very quickly. Okay. Now, on the, or is it on the equator? I'm not sure. But pretty close to being on the equator, somewhere in North Africa, Siena, okay? There is a well. And it's very deep, or it was very deep in 276 BC, right? Let's say 200 BC. So that well is so deep that the sun would come overhead, so it must be on the equator, and directly overhead at midday, the sun's reflection could be seen 300 feet down. That meant the sun was exactly overhead. Now, it was also known that directly at midday, but slightly south, right? So the sun is moving this way, but you can move south. You can still plot when the sun is exactly overhead just by moving south. But when you move south, you come across an obelisk. And the obelisk at this particular time used to cast a shadow. Now wait a minute, the sun is directly overhead here, but it's casting a shadow here. So you can set up triangulation. Why is it not casting a shadow when it's up here? No, it's directly overhead, but there's a shadow down here, and you can take up this triangle, this one here, and figure out the angles and the lengths and the sides and the hypotenuse, this, that, and the other, and project it. And look for the similar triangles. I don't know exactly where they are here. And using similar triangles, measure this bit here and this bit here. And just using ordinary geometry that's been figured out by Pythagoras and the Greeks, find the radius of the Earth. And Eratosthenes found that radius pretty closely, okay? In particular units of the time. So that's our first step. So let's get rid of that. Now it's a pity we didn't inherit Archimedes' work, but it was mostly burnt when the Romans burnt the library of Alexandria. We probably would have had calculus way before we did. The next thing we go to Galileo. Now the first thing that Galileo did that was important was, well, he studied free fall, okay? Objects fall freely. He noticed that, or at least he proclaimed that, he was capable of taking air resistance out of the picture in his own mind. And he watched the lamp in a cathedral do something. We'll talk about that in a minute. So according to Galileo, all objects, that means all things with mass, whatever that is, fall at the same rate. Now that doesn't mean, you know, if you drop one ball and another ball here, one won't hit the ground before the other, because you can't drop them exactly at the same time, but they will stay in unison. They won't catch up with each other. So we eliminate air resistance from the equation, and we will say that all objects fall the same rate. Galileo actually rolled objects down an incline to make it easier to measure things. But wait a minute, before Galileo, nobody was able to measure anything when it came to measuring time, because they only had water clocks, egg timer type sand clocks and things like that, or the daily motions of the sun. Galileo invented a great timer, the pendulum. So Galileo invented the pendulum, and he noticed that the only thing that affected the period, that's the time for a full swing. It's kind of like an oval. The time for the pendulum to make a complete cycle is called the period. Now, he could measure the period experimentally and say that was constant, but it was proportional just to the length square rooted and the acceleration due to gravity. But for Galileo's purpose, he just knew that t squared is some number times the length, and that was good, right? So he could time things, and he studied free fall, and he essentially came up with the idea of inertial mass, the tendency of objects to keep on moving unless acted upon by something. Well, Galileo didn't quite know what the something was. That took Newton. Now wait a minute, that's the beginnings of all of physics, really. Natural philosophy, I like to call it. He quantified his results, and that made a huge difference. A lot of people credit him with the invention of the scientific method. Scientific method isn't used much in physics. It's used in biology and stuff. In other words, hypothesis. Newton says, I don't frame hypothesis. He doesn't. Okay, so Newton is the next character. Now Newton has done many things, such as Newton's law of cooling, optics, many things. But we're talking about here his law of inertia. Actually, it's Galileo's. The tendency of objects to move away in a straight line not a circle, unless acted upon by an outside force. And force is mass times acceleration. Now for us, in SI units, kilograms are the units of mass, and meters per second are the units of speed per second. You're changing your speed per second. I'm assuming a little bit of knowledge of this stuff. So kilograms meters over second squared are newtons. So if you can make 1 kilogram accelerate at the rate of 1 meter per second every second, in other words, if you push a kilogram, right, on a frictionless surface and it changes speed by 1 meter per second every second, like this, you're going 1 meter per second, 2 meters per second, 3 meters per second, then you are exerting a force of 1 Newton on it. Now here's another one. If you jump off the Empire State Building, roughly speaking, after 1 second of free fall in the absence of air resistance, you would be traveling at a speed of 32 feet per second. After 2 seconds, you would be traveling at a speed of 64 feet per second, and so on. 96 feet per second. So, in meters per second, that is closer to 10 meters per second after the first second, 20 meters per second after the second second. It's closer to 9.8 meters per second squared, and so on. So after 10 seconds, you're doing 100 meters per second as a speed in free fall, right? That's what Galileo's big discovery was, the acceleration due to gravity close to the surface of the Earth. Somewhere else it'll be something else. So Newton identified the idea of a force as the thing necessary to change the natural motion of a body. Make it go round in a circle, you need a force. Make it go round a corner, you need to push it. Change its direction, you need to push it or pull it. To get it to go quicker, you need to push it or pull it. To stop it, slow it down, you need to push it or pull it. Force equals mass times acceleration. Newton's third law. These are the motion laws of Newton, by the way. For every action, there's an equal and opposite reaction. Now, some people say that if you're standing on the floor is acting at the same rate up here. That's one way of looking at it. For me, I think of this one as being the conservation of momentum. Wasn't quite there when Newton was around, but it means this. If you have 2 ice skaters on the ice rink and you push one away, if this one has a mass of 60 kilograms and this one has a mass of 30 kilograms, they both go away, but they both carry the same momentum each, but one's speed is twice the other, right? The light object is going twice as quick as the heavy object. It's the same thing in the recoil of a gun. The gun recoils backwards and the bullet goes forward, but the bullet goes forward much quicker than the gun recoils backwards. So if you fill a rifle, the stock of a rifle with lead, you'll feel less recoil. All right, Newton invented calculus to work out the laws of gravity, and calculus was independently worked on by Leibniz. Incidentally, Leibniz is one of the guys I could have put in here. There were several Leibnizes. One was a dad, and he had a doctoral student, Gottfried Leibniz. All right, so gravity is part of the whole thing here, and the idea of a force, we'll carry that on now in a minute. So, strictly speaking, you guys have to catch up with a little bit of physics, but I'm assuming, let's say, 8th or 10th grade physics. And here's what we should know from 8th or 10th grade physics. If you don't know them, by the way, you can go back and look at some of my lectures, but you get all this stuff in the books. Now, I'm not going into the idea of vectors here, it's not necessary. Mass times velocity, and has units of kilograms, meters over a second, is called momentum. And force is mass times acceleration. Now, kinetic energy, everything moving has kinetic energy, and you can work out how much kinetic energy it has. I actually have done it, so I'll go back to one of my lectures. Kinetic energy, the formula for it is a half mv squared. It's a scalar, never be a vector. Now, kinetic energy comes usually with a half mv squared, and that's it. Or it could be a half I omega squared. One way or another, it's a speed squared and a mass thing. So potential energy can show up in many different ways. The potential energy of a compressed spring is a half kx squared. For us, the potential energy is going to be just above the surface of the Earth. If I use a force to raise a mass, height of h meters, the work done is force times distance. Work done for anything is force times distance. S is distance. Now the force of gravity is mass times acceleration. And the acceleration involved when we're considering gravity is that what I talked about a minute ago, the 10 meters per second squared. On the surface of the Earth, that is. The gravity force on the surface of the Earth is mass times acceleration, just like anything else. But the acceleration due to gravity on the surface of the Earth is 10 meters per second squared. So what is the weight of 5 kilograms? The weight of 5 kilograms is the force of gravity on 5 kilograms. Well, the weight of 5 kilograms is 10 newtons. So roughly speaking, if you want to get from kilograms to weight, in other words, mass to weight of force of gravity, just multiply by 10, all right? A 60 kilogram person, okay, that's 600 newtons approximately, and so on and so forth, right? Kilograms meters over second squared are newtons. So potential energy for us is just going to be mgh. Force of gravity times the distance moved. So that's the h. So I'll let you get your hands around that. This is all we need. Now Newton's law of gravity. Newton said, well, it's easy to work this one out as well. This gravity force, if you have something here, it has the mass of the Earth on it, and we have a 5 kilogram mass on the surface of the Earth. If I double the 5 kilogram mass, I'll double the force of gravity, right? Quadruple it and so on. So the force of gravity between two gravitating objects, this one and this one, is going to be something to do with their masses. Actually, it is going to be the product of their masses. And as you pull one mass away from the other, the force of gravity gets smaller. Actually, it gets smaller in proportion to the surface area of a sphere. Surface area of a sphere grows by 4 pi r squared. We're going to absorb that 4 pi into a number that we're going to not worry about, but we're going to say that the force decreases in proportion to the square of the distance because of this growing surface area of a sphere. Now, in practice, if you take a 1 kilogram mass and a 1 kilogram mass, and separate them up by a distance of 1 meter, okay, you do not get a force of 1 Newton. This is what you get. You get a force of 6.67 by 10 to the power of minus 11 newtons. Now this was first measured by Henry Cavendish in 1798 after Newton was dead, and it plays a big role in actual calculations using Newton's law of gravity. So to correct this equation, to make sure that every time we plug in numbers of kilograms and meters, we have to put in this G. And this G is not the same as the little g. Little g is the acceleration due to gravity on the surface of the Earth. The big G is called the universal constant of gravitation. It's said to be universal because it means that if you go up to Jupiter, it has the same value. If you go to Alpha Centauri, it has the same value. And if you go to the edge of the universe, it's supposed to have the same value. Maybe it changes, we're not sure. But close to at least within our galactic area, the G has this value of 6.67 by 10 to the power of minus 11 Newton meter squared over kilograms. Now that was measured by Henry Cavendish, and there's a link here, using a torsion balance invented by John Michel, or actually was it? Yes, and then this torsion balance was given by Michel to Charles Augustus Coulomb. There is another force in nature. It's the electric force. Newton had written down a force law for gravity. Turns out that if you take electric charges, you get a force law that's very similar, but except instead of mass, you have charges. And instead of little g, you have an electric constant, right? Now the torsion balance works very neatly. Cavendish used the torsion balance to measure the G, and Coulomb used the torsion balance to measure the electric constant. It was all in vogue at the time. People were very interested in these things, and they had some money, and if they didn't have money, they had sponsorship. Now Newton's law was put in there to make sure that Kepler's laws could be figured out. Kepler has 3 laws of motion. Kepler's laws, what are they now? 1, the planets execute elliptical shapes of motion, orbits if you like, around the sun. Kepler was devastated when he found out that the shapes of the orbits were ellipses. They're not perfect. He thought because God had made up this system that they should be perfect circles, and he was devastated, but no, they're ellipses. Comets can make an elliptical orbit, but some comets might come and go and never come back again, so that the thing is open, right? Some orbits could actually be circular. One way or another, the shapes of these orbits are ellipses, circles, hyperbolas or parabolas, and these are well-known solutions to certain types of equations. They're called conic sections. The shapes of orbits are conic sections. One way or another, our Earth orbit is pretty close to being circular, slightly off, slightly elliptical. So far so good, we're moving ahead. You guys don't have to do any calculations. Now the whole idea of inertial mass is in here, and we're going to talk about that in a minute. So we have a law for the force of gravity. Force of gravity between any 2 objects a distance apart we make them a big object. For example, it could be the Earth, and this could be a satellite, or it could be a person, or it could be a person sitting on the surface right there, okay? This R is that distance or this distance. This is an M, and this is an M, and they're little m's. And the big M, they're both gravitating mutually. This one is pulling this one, and this one is pulling this one, just that the bigger one seems to pull more. All right. So, like everything else, Force is mass times acceleration. In other words, the little m feels an acceleration due to gravity. Acceleration due to gravity we write usually as a g. The little m appears in here as well. And the question is, can we cancel them? That's a very big question. According to Yoke-Foss's experiment and the principle of equivalence, we can. What does that mean? This mass in here is defined in terms of the pull of gravity between these two masses. This one is not. This is defined in terms of if you go up to a piece of lead and you try to kick it, it resists your push. You could hurt your foot. It's inertial. But we're going to say for now that we can cancel. They are equivalent, okay? Now we need an expression for potential energy. Sorry. Potential energy we said a minute ago was mgh. Now suppose a mass is in orbit, or somehow it's up here, the distance this much above the surface of the Earth. So it's from here to here, it's the total distance r between the center of this mass and the center of the Earth. That's how much work we took. We took this mass and we dragged it all the way up to here. We're doing a certain amount of work. Force times distance. Now this is a casual way of looking at it, but it works. Now the force we're exerting on it is the force we're overcoming is the force of gravity, and we move at a distance r. Now let's see what this is. Okay. We have here an expression for g. Because I said we can cancel the two masses. The mass gets cancelled. The expression for g is gm over r squared. I'll write it more clearly. Or I could have just said the work done is force times distance, force times the height. Well, there's the force and there's the distance. Well, we have an r here and an r there, so one part cancels. So now I have an expression for potential energy, and we also have for anything at all. The kinetic energy is mv squared over 2, all right? Nothing about relativity. Nothing is needed yet, all right? So that's all I wanted from this whole business of classical mechanics. Now, there is a thing called the escape velocity. If I have enough kinetic energy to overcome the gravitational pull of an object, now here's something. Here's something that's bound gravitationally. We'll make a circular or an elliptical orbit. But if I have enough kinetic energy, I can overcome this and spiral off into space, right? In other words, I can escape the gravitational pull if the kinetic energy is equal to or slightly bigger than the potential energy. We'll say it's equal. So the potential energy, kinetic energy, slightly greater than the potential energy. Now we're going to say we can cancel the masses again. Now I have an expression for the escape velocity that allows an object to escape the gravitational pull of something, right? Now John Michel said, let's ask a particular question about this escape velocity. So I want you to get over this one here. We're going to hang on to this all the time. V squared equals 2gm over r. We won't bother with the square root. V squared, the escape speed, is 2gm over r. I'm going to clean the board right now. Now this is a mass, a gravitating mass of radius r, and the escape velocity from this is 2gm over r. Now I don't know what the speed, on the surface of the Earth you can work out what the escape speed is approximately. It's probably 25,000 miles per hour or something, I'm not sure. Now let's take the speed of light measured by Christian Huygens and Romer, and around that time it was found to be pretty close to what it is, 186,000 miles per second. Well, that's the same as 300,000 meters per second. I get tired writing all these, so I'll say 3 followed by 8 zeros. So this is the speed of light, measured in many different ways and measured now accurately. You can measure it at home using the radio. You get a piece of metal. I'll show you that another day. So the speed of light, okay, that means this. Okay, so at the speed of light, if you're traveling at the speed of light, after 1 second, you're approximately at the moon, right? 220,000 miles away. Approximately 200,000 miles away. Traveling for 8 minutes. Where are we? At the sun, right? If we switched off the sun, and I'll ask this question in a different way later, if we switched off the sun, somebody switched off the sun, we would not know about it until 8 minutes later. All right. Traveling at the speed of light for another 4 years. Where are we? We're at our nearest star, Alpha Centauri. Traveling at the speed of light for 100,000 years. We're at the edge of the galaxy. Now I forget what it takes to get to the edge of the universe. I could work it out. Actually, I have worked it out somewhere on this stuff as well. I just don't keep that number in my head. So, There is the possibility, said John Michel. John Michel said, suppose an object has enough mass in it with a certain radius so that its escape velocity is equal to or greater than the speed of light, then it stays dark. We won't be able to see it. That's what he said. John Michel says there may exist dark stars out there because they're dark because light can't escape from them. This escape velocity on their surface is greater than the speed of light. I've got an interesting question, by the way. When it comes to talking more about black holes, it's possible to shatter the whole idea. But never mind about that. All right, so the speed of light. Suppose the speed of light is denoted by c. Then I can write down the escape velocity is equal to c. And I can write down the escape velocity equation and say that this speed of light squared is 2gm over r. Now this is the actual condition for a dark star. It's also the condition for something to be a Schwarzschild black hole. I'm going to look into that now, right now. Okay, so this was left on the shelf until general relativity came out. I don't know why. So general relativity came out and we have Einstein's field equations. And a specific set of those field equations in vacuum, I'll write it down. This is all we have to capture. All the talk that I've done so far just captures this equation. So if you've got a headache with the math up to now, and don't worry about the units, this is all I need to get out of it, right? Now I'm going to rearrange this equation. So I divide both sides by c squared. And now I'm multiplying both sides by r. I'm going to call this RRS. All I did was take the exact result here and put the r outside on the left-hand side with the c squared downstairs. There. This thing is called the Schwarzschild radius. We'll get to it in a minute. There's a set of complicated equations which in shorthand are written r mu nu equals 0. R mu nu is a Ricci tensor. In vacuum, for a spherically symmetric spherical mass gravitating in vacuum, it says that there is a special geometry for this, okay? And it's called the Schwarzschild geometry. And it's for an object that is not rotating, has no electric charge, and no deformities in it. And it says this, all right. It says that a little tiny distance between any 2 points in this space has a certain formula to it. Here's something. Pythagoras' theorem for a finite length says that x squared plus y squared is L squared. for a little triangle, let's say. Now this could be a little triangle too, with a radius and an angle, right? So this is like d theta, dr, and so on and so forth. Now I forget this one. Now I'm going to have to clean this. I'm going to write this down and keep it up here. No, it's going to be like this, actually. Now, the solution to this one which was found by Schwarzschild, is called the Schwarzschild solution. And it has a term in it that looks like this. Now, here's where things go funny. That's what general relativity or Riemannian geometry just gives us. To get it to match up with Newton's theory of gravity, you have to put in the numbers by hand. So really Newton is still steering the show. Really, this is what's happening. This r is 2gm over c squared. This lambda is put in by hand. To make sure that the theory of general relativity gives the same escape velocity that Isaac Newton gives. So who's winning here? Well, general relativity is not giving us, it just gives us a constant. We have to put this in by hand. Now, this whole thing can be rearranged. So that we get a black hole when this term becomes zero. Strange things happen. You divide by zero, you get infinity. You multiply by zero, you get nothing, right? So the black hole condition is that 1 that term is zero. We can rearrange this. Let's multiply both sides by r. Now that is absolutely all we get out of general relativity looking at the Schwarzschild solution. But wait a minute, John Michel got this years ago, yeah? I don't know, let's say 1700 or something, let's say 1760 or something, whatever like that. One way or another, this is the Schwarzschild radius for any gravitating object. Now what does it mean? What does it mean? It means that the mass gets big enough or the radius gets small enough. So what we're going to do is we're going to look at our sun and we're going to make its radius small and calculate what radius the sun would have to shrink to in order to become a black hole. Now that means an object from which light cannot escape. Let's do that. So I need to clean the board and we'll remember our Schwarzschild radius. It's the radius of a dark star. Okay, what does that mean? Now I don't know what I forget what the radius of the sun is. I don't know. Is it 10 to the power of 8 meters? Doesn't matter anyway. If the nuclear reactions in the sun suddenly stopped, right, there wouldn't be pressure enough to stop that thing from falling in under its own weight. The radiation pressure, the nuclear reactions pressure, would no longer hold it out as a big sphere. And it could, in theory, shrink. Very large stars, if they hit the Oppenheimer-Volkoff limit, can do that, right? So this R will shrink down to become some other R, which is going to be much smaller. Now what's happening? None of the mass is disappearing. The density of the sun is increasing. You're getting denser. You're squashing it in. The density is increasing, but the mass is staying the same, right? So that the pull of gravity on the surface is getting much bigger. You have a really concentrated mass dragging everything into it, okay? The question is, just at when it begins to stop light from getting out, what is the radius? That radius is called the Schwarzschild radius for our sun, and we'll figure it out. We work out the Schwarzschild radius. We'll do it simply by putting in all the numbers. The mass of the sun is 2 by 10 to the power of 30 kilograms. The G and the C. I'm putting in all the units to be pedantic. So I get that, okay? All right, so I'll divide the 3 into this one first. And I multiply this by, let's see, did I get that right? 3, oh this has to be, this becomes 9, I made a mistake. So it becomes, I'll multiply this by 2. Now, 2 7s 14, 2 6s 12, and 1 is 13. 2 6s 12, and 1 is 13. And 10 to the power of minus 11 plus 30 all over okay, all right, so now we have, I have to multiply this by 2 as well. And I figured out all the units are going to be, when you cancel out all the units, I won't do it on the board, but it's going to give me meters. You can check. 1 kilograms here, and kilograms are in here, and meters squared here, per second squared cancels with those ones in there, and you're just left with the meters, all right? So when I work out all of this, I get approximately 3,000 meters, or 3 kilometers. And what does that tell me? That means that the sun would shrink down to about the length of, or the width of Manhattan, right? 3 kilometers, 3,000 meters. That's how much the sun has to shrink before it stops light from getting out of it. Now that's the beginning of black holes. The rest is kind of other stuff that happens when you look closely at Schwarzschild geometry and then Kerr-Newman geometry and other things that complicate things. But I've got a question to throw at you, okay? I was at a lecture by S.J. Gates Jr., great physicist, when he came to Embry-Riddle. Actually, I tried to get him there. It was me, I was working on stuff at the time. Now, what happened? Jim Gates comes to Embry-Riddle and he gives a lecture on black holes. And he says, this is what happens. So Jim says, we have the Earth. In orbit around the sun. Now a minute ago I said that if the sun switched off its light, or somebody switched off the sun, it would be 8 minutes before we know about it. Because light propagates at the speed of c from here to here, a distance of 8 light minutes. Now Jim says, gravity does the same thing. Gravity propagates at the speed of light. Gee, I didn't know that. At least I did, I wasn't thinking about it. Because if gravity propagates at the speed of light, something interesting should happen. Suppose the sun hits its Schwarzschild. Okay, if somebody got rid of the sun, it would be 8 minutes before we started heading off into outer space on a tangential orbit, tangent to our orbit, because we won't feel the lack of the gravitational force for at least another 8 minutes. So the Earth would have gone, let's say, from here to here in 8 minutes. Now here's the sun, if it meets its Schwarzschild radius, okay? And at the Schwarzschild radius, no light can escape because the escape velocity has been reached, so light can't get out, right? Maybe this escape velocity is bigger than the escape of light, the speed of light, so it's really seriously trapped. But wait a minute, what about gravity? Gravity can't get out either. The escape velocity as gravity is the speed of light, so it can't get out. That tells me that you could walk right up to the surface of a black hole and put your hand right up to it and you don't feel anything, right? Is that true? I don't know, I've never done it. But there's an inconsistency there somewhere. I haven't figured out, and I haven't seen anybody else figure it out either. If the escape velocity is if the speed of light is the speed of gravity, in other words, the speed at which gravity propagates, it may not be. If that's the case, it has to be considered. And, you know, would gravity leave the sun if it becomes a Schwarzschild black hole? I don't know. So I leave it with that, and I'll see if I can get all this stuff on the web. I think I've gone over it. I found a way to get an hour's lecture on the web. I hope it works.